Dear students, welcome to yet another online tutorial on Principles of Communication System. Now we are into module 2 and we were discussing about angle modulation. So in previous session we discussed in detail about FM, specifically single tone FM, right? And we have obtained the time domain expression for single tone FM, and also I have introduced you to some parameters such as frequency deviation and modulation index, and we have seen based on the modulation index value beta, right, we can divide the single tone FM into two cases. The first one is narrow band FM and the other one is wideband FM. So whenever this beta is very small compared to 1 radian, so that particular approximation of single tone FM can be considered as narrow band FM. So we have seen this narrow band FM, it is comparable to that of a single tone AM with carrier, right? And the other case which we have to discuss in today's session is wideband FM. So this approximation, this wideband FM is when beta is large compared to 1 radian. So when beta is large compared to 1 radian, we cannot apply the approximation of beta being small. So then this wideband FM can be considered as a particular case of single tone FM for any arbitrary value of beta, right? So this is what we are going to discuss in today's session. So those who missed out previous session and those who have some lack of clarity in these aspects which I have discussed now, I request them to please revisit the previous video and come back and watch this, right? So we'll start with a wideband FM, right? So we have seen a single tone FM where M of t is a single frequency sinusoid, that is AM cos 2 pi FM t, right? The wideband FM signal, we can write it as S of t is equal to AC cos 2 pi FCT plus beta times sine 2 pi FMT. So we have seen this in last session, right? So this is the time domain expression for a single tone FM, where we have seen beta is equal to delta F by FM, and delta F in turn is actually what, KF into AM. So beta is delta F by FM. So these aspects also we have seen. So what we'll do is we will start from this particular time domain expression for single tone FM and try and derive the spectrum of wideband FM. That is what we are going to do today. So for this there are some certain mathematical prerequisites. So as and when required, I will be discussing those things. So we'll start with the time domain expression for single tone FM. So S of t, as I have written here, it is AC cos 2 pi FCT plus beta sine 2 pi FMT. So this is S of t. So now now we need to have a prerequisite, right? So e power j theta by Euler's equation, we can write as cos theta plus j sin theta. So from this we can say cos theta can be written as real part of e power j theta and sin theta can be written as imaginary part of e power j theta. So we have here cosine of something. So if you consider this entire thing as theta, right? So I can write S of t as real part of AC times e power j. Instead of theta, I have this entire thing, so I'll write it as 2 pi FCT plus beta sine 2 pi FMT, right? So this is, so I can write S of t as real part of AC e power j 2 pi FCT plus beta sine 2 pi FMT. So now I can further rewrite it as, so as you know, e power j times a plus b, it will be equal to e power j a into e power jb. So I am going to apply this result here. Right, I'm going to apply this result here. So I can write, I do have e power j 2 pi fct plus beta sine 2 pi fmt. So this, if I consider this as a and this as b, I can rewrite it as, I'm just rewriting and rearranging. So I can rewrite it as real part of ac times, I'm just writing the e power j beta sine 2 pi fmt term first into e power j 2 pi fct. So I'm just rewriting it like this. Right. So now the first term, that is ac times e power j sine 2 pi fmt. Right. So this is actually this entire thing is s of t. So this ac times e power j beta sine 2 pi fmt. Like if we exclude this e power j 2 pi fct from inside the argument of real part of, right. So we'll get this. So I can call it as s tilde of t, right. That is ac e power j beta sine 2 pi fmt, right. This s tilde of t, it is nothing but complex envelope of s of t. So in detailed about this complex envelope we will be studying in 6th semester, right. But for instance, like I'll give you a brief idea about what actually is complex envelope, right. So this s of t, it is our modulated signal. It is a real valued and band pass signal, right. It's a real valued band pass signal, right. So what we can do is by means of frequency translation, what we can do is this, any real valued bandpass signal can be represented as a low pass equivalent, a complex low pass equivalent signal, right. So that is actually what complex envelope. So for instance, you can just note this down, right. So complex envelope of any real valued signal is the low pass equivalent of the signal. So I'm not discussing in detail how a complex envelope can be obtained, but by seeing this, so to obtain complex envelope, what we need to do is, if it is cosine or sine, we should write it as either real part or imaginary part of complex exponential, right. Then from that, if we suppress this e power j omega t or e power j 2 pi fct term, right, and if we suppress this real part, right, so whatever is left out, that will be complex envelope. So this is actually s tilde of t, we call it a complex envelope of a real valued bandpass signal. So this is a very important aspect here. So we'll be using this concept, right, to obtain the Fourier transform of s of t. So if s of t, it is real valued and bandpass, but s tilde of t, it is complex, right. S tilde of t, it is complex, as from the expression itself we can make out. So it is complex and it is low pass, it is complex and it is low pass, right. And apart from that, if you see this, you can see, if you expand e power j something as cos something plus j sin something, you will also get to know it is periodic, right. It is periodic. So what we can do is, I'll write s of t in terms of s tilde of t now, right. So now s of t can be written as real part of the first term, that is ac e power j sin beta fmt, right. I am writing it as s tilde of t, and whatever is left out is e power j 2 pi fct. So this is how I can represent s of t, right? So s of t is this, so maybe I'll call it equation number, say, 1, right? So we'll come to it later. So now from now on, what we'll do is we'll consider this s tilde of t, right? S tilde of t is a as I mentioned, it is complex, low pass and periodic signal, right? So for this you can see s tilde of t is periodic, right? It is periodic with fundamental frequency equal to Fm, right? So it is evident from this expression. If you expand this e power j beta sine 2 pi Fm t as cos beta sine 2 pi Fm t plus j sine beta times 2 pi Fm t. So we'll get a sinusoid, and the frequency of that will be Fm. So that's why I mentioned s tilde of t is a periodic function with fundamental frequency is equal to Fm. So this Fm will be actually what? 1 by the 1 by time period, right? 1 by fundamental time period, right? So this is s tilde of t. So now what we need to do is we need to obtain the Fourier transform or spectrum of this. We need to obtain spectrum of s of t, right? So but instead of obtaining spectrum of s of t, right, what we'll do is we'll obtain the spectrum of s tilde of t, that is the complex envelope or complex low pass equivalent of s of t, right? Then if we multiply s tilde of t with e power j 2 pi fct, so you can see by frequency shifting property of Fourier transform, multiplication with e power plus j 2 pi fct will be actually what? Shifting right by an amount fc in frequency domain. So using that idea we will find out the spectrum of s of t. So that is what we are going to do, right? So now as s tilde of t is periodic with fundamental frequency Fm, what we can do is we can represent, right? So one more statement I would like to make now. Any periodic signal can be approximated using Fourier series expansion. So any periodic signal, for instance, while we discussed about ring modulator and balance modulator and all, what we did is actually we had square pulse trains. Those were periodic signals. So we have represented it as actually what? Weighted sum of sinusoids and cosinusoids. So similarly, any periodic signal can be approximated or represented using Fourier series expansion, right? So similarly, s tilde of t also can be represented using Fourier series expansion, and Fourier series expansion of s tilde of t, it will be equal to, right, summation n from minus infinity to plus infinity Cn times e power j 2 pi n Fm t. So this is how you can represent, maybe you can represent s tilde of t using Fourier series expansion, where Cn are Fourier series coefficients, right? So you have studied this in smaller semesters, right? So so Cn are Fourier series coefficients. So and Cn can be obtained as, so any periodic signal with period t, right? So the Fourier series coefficients can be obtained as, in general, 1 by t integral minus t by 2 to plus t by 2, then s tilde of t times e power minus j 2 pi n Fm t, then dt. This is how you can obtain this Fourier series coefficient, the Cn's, right? Where this t is nothing but what? 1 by fm here, or 1 by fm is equal to t, or 1 by t is equal to fm. So if I substitute it here, I will get fm times integral minus t by 2 will become actually what, minus 1 by 2 fm, and plus t by 2 will become 1 by 2 fm, right? So integral minus 1 by 2 fm to 1 by 2 fm, it is s tilde of t times then e power, yeah, so I have written here fm itself, so I don't have to change that, e power minus j 2 pi n fm t dt. So this is the Fourier series. This is how we can find the Fourier series coefficients. So now what we can do is we can try and find out the Fourier series coefficients of s tilde of t. So s tilde of t, in turn, it is equal to summation n from minus infinity to infinity cn e power j 2 pi fm t, and that is also equal to, we have seen here, AC e power j beta sine 2 pi fm t. So now if I substitute this value of s tilde of t in the expression for Cn, right, and simplify that, we will get the general expression for Cn. So we'll do that. So Cn is equal to fm times integral minus 1 by 2 fm to 1 by 2 fm, right? S tilde of t is AC e power j beta sine 2 pi fm t, right, into e power minus j 2 pi n times fm t dt. So this is how we can find the Fourier series coefficient. So now further, right, I can rearrange it. So I have AC is a constant, we can take it out, so we can write AC into fm times integral minus 1 by 2 fm to 1 by 2 fm, right? So e power j something times e power minus j something. So what I can do is I can just take that common, e power j, and write beta sine 2 pi fm t minus if it is n times 2 pi fm t dt. So we have this integral AC times fm integral minus 1 by 2 fm to plus 1 by 2 fm e power j beta sine 2 pi fm t minus n 2 pi fm t dt. So in this, so this is actually Cn, that is the nth Fourier series coefficient, right? So in this, if you substitute x is equal to 2 pi fm t, I am going to make this substitution. Instead of 2 pi fm t, I am going to make a substitution x. So I'll get dx by dt will be equal to 2 pi fm, which implies, right, dt. So this dt, whenever I am making substitution, right, this dt will change. Also this, instead of sine 2 pi fm, in this, instead of 2 pi fm t, if I substitute x, right, here again if I substitute x, right, so this dt will change, and of course the limits will change. So we should find out what are those. So dt is equal to, you can write dx divided by 2 pi fm. So also we should find out what will happen to limits, right? So we can see whenever t is equal to minus 1 by 2 fm, right? So when t is minus 1 by 2 fm, so we'll get x is equal to minus pi. If we can write x is equal to minus pi, and whenever t is equal to plus 1 by 2 fm, you will get x is equal to plus pi. So if you make these substitutions in this, so we have to change the limits. Also, instead of dt, dx should come, and 2 pi fmt should be replaced with x. There is a reason why we are doing this, right? So this, then this integral will reduced to a standard form, so which we'll see soon that into a Bessel's function, right? So we rewrite this. So now Cn is equal to, anyhow this dt will be nothing but what, dx by 2 pi fm. So this 2 pi fm which is inside the integral, which is being constant, I can take it out. So I'll write it as AC fm divided by 2 pi fm times integral, instead of the lower limit minus 1 by 2 fm, I should write minus pi, and instead of the upper limit plus 1 by 2 fm, I should write plus pi, right? Then e power j beta, right? So I'll write it as beta sine, instead of 2 pi fmt, I should write x, and minus n times again x, right, times dx. So I will get this now. So in this, what happens is this fm and fm gets cancelled, right? So I can once again rewrite this. It is AC into 1 by 2 pi times integral minus pi to pi e power j beta sin x minus nx dx. So this particular integral 1 by 2 pi into minus pi to pi e power j beta sin x minus nx, right? So that is a standard integral, right? So I can replace that integral with Bessel's function, right? An nth order Bessel's function with argument equal to beta. So this integral, so 1 by 2 pi integral minus pi to pi e power j beta sin x minus nx dx. So this integral, right? So this integral is a nth order Bessel's function with argument as beta. This is actually of first kind, right? So this is actually what Bessel's function of first kind, right? So the values of Bessel's functions, actually what they are standard, just like how you have the normal distribution table. So we can have actually what the standard values of Bessel's function. So we do have some interrelations. While discussing problem, I'll discuss on Bessel's function in detail, right? But for instance, what we can do is this particular integral 1 by 2 pi, this entire thing, right? This entire integral can be replaced with an nth order Bessel's function. For what actually is this n? This n is whatever is coming along with this actually what x, right? And argument, when I say argument is beta, right? This beta is whatever is coming along with sin x, right? So this beta sin x minus nx, it is the argument of complex exponential, right? So inside that, the order is actually what the coefficient of x, and the argument is actually what the coefficient of sin x, right? So this is a nth order Bessel's function. So this is actually what a solution of a particular kind of actually what second order differential equation, which is called Bessel's equation. You might have studied it in math, right? But we don't have to dig that much into deeper. So for instance, right, please appreciate, we can rewrite this particular integral using a first kind nth order Bessel's function with argument equal to beta. So now I'll rewrite the Fourier series coefficient Cn as AC times J n of beta. So I can rewrite the Fourier series coefficient as AC times Jn of beta. Now if I can substitute this, right, if I can substitute this in the expression for Fourier series expansion of S tilde of t, that is complex exponential, right? So we know s tilde of t, it is equal to summation n from minus infinity to infinity cn e power j 2 pi n fm t, right? So if you substitute this value of cn here, right, then we'll get right, s tilde of t, right, s tilde of t. So that's what I'm going to do now. So s tilde of t is equal to summation n from minus infinity to infinity, right, ac times jn of beta times e power j 2 pi n times fmt, right? So this is s tilde of t. So now we do have this s tilde of t. Now if you substitute this s tilde of t in equation number 1, so if you remember what is equation number 1, equation number 1 was that of s of t, right? So now substituting s tilde of t in expression of s of t. So if you remember, the expression of s of t was s of t is equal to real part of s tilde of t into e power j 2 pi fc t. This was actually what the expression for s of t. So now in this expression, if I substitute the value of s tilde of t given by this equation, I'll call it equation number 2, right? So we'll do that. So as it is a recorded session, I am going a bit fast, right? So please take some time and watch these derivations step by step, which is very important, right? So I'll just write s of t is equal to real part of, now s tilde of t, just now we found out, right? S tilde of t is nothing but what? Summation, right? S tilde of t is nothing but what? Summation n from minus infinity to infinity, right, ac times jn beta times e power j 2 pi n fm t, right? So this entire thing is s tilde of t, that should be multiplied with this e power j 2 pi fct. So that is multiplied with e power j 2 pi fct. So this is now the s of t, right? So now as this taking real part and summation, as they are actually what? Linear operators, we can just rearrange right, we can just rearrange their order, but before that I would like to make some more simplification, right? So we have 2 e power j terms here, right? We do have 2 e power j terms here, right? So what I'll do is, it is equal to real part of, right, and maybe ac also we can take out, so ac we can take out, right? So I'll write is equal to ac into real part of, and this, as this j n beta, it's actually what? A function of n, I can't take it out, right? So summation n equal to minus infinity to infinity j n beta times, I get e power okay j, so it is 2 pi t is common, so I'll get, right, e power j 2 pi times fc plus n fm times t. We can rewrite it like this, excuse me. So it is e power j fc times n fm times t. So now what we can do is, I can order the summation and the real part, right? So this is e power j something, right? So e power j something, as I told earlier itself, e power j something, if that something is theta, it is equal to cos theta plus j sin theta, and real part of e power j something, if I say real part of e power j something, that will be cos of something, right? That something is actually what? Argument of e power j, right? Whatever is argument of e power j. So if I rearrange this, so I'll rewrite it, right? So s of t, again I'll write s of t is equal to ac times, right? So I'll just order the summation and real part rotation. So summation n from minus infinity to infinity, right? Jn of beta times real part of e power j 2 pi fc plus n fm times t, right? So now real part of this will be nothing but what? Cosine of this entire thing. So this, if you consider 2 pi times fc plus n fm times t as theta, right? If you consider this as theta, right, then real part of e power j theta will be cos theta, right? So we can straight away write that. Right? So it is equal to AC times summation n from minus infinity to infinity Jn beta times cosine of 2 pi. So maybe I'll use a square bracket here. 2 pi times fc plus n fm times t. So this is what we have. So this is actually what? S of t, right? So now we have represented S of t as weighted sum of certain cosinusoids, right? So where n is spanning from minus infinity to infinity. So now I can expand S of t as weighted sum of some cosinusoid. So the weight of each cosinusoid will be AC times j n beta, right? The weight of nth cosinusoid will be AC times j n beta, right? So that is what we have now. So now, right, so I'll consider we consider this as an intermediate result, right? We'll consider this as an intermediate result. So this we have. Now what we need to do is we need to find the spectrum of this, right? So we need to find spectrum of this, right? For that we can apply Fourier transform on both sides, right? So to obtain spectrum of S of t, we need to apply Fourier transform on both sides. So I'll name this as equation number 3, right? So if you apply Fourier transform on both sides, this of S of t will become capital S of f. Sorry, S of t will become capital S of f. That is equal to AC times, right, summation n from minus infinity to infinity, right? So this j and beta, it's a constant, right? So for a particular beta, j and beta will be and j and beta will be a constant, right? So I am writing j and beta as such, right? Now what is the Fourier transform of cos 2 pi fct, right? What is the Fourier transform of cos 2 pi fct, right? Or what is the, right? So we have seen Fourier transform of cos 2 pi fct. So we have already seen it many times, right? So right, so we have already seen it many times. The Fourier transform of cos 2 pi fct will be it is half del of f minus fc plus half del of f plus fc, right? So Fourier transform of cos 2 pi fct, right? Fourier transform of cosinusoid of frequency fc will be 2 impulse functions weighted by half on plus fc and minus fc. So we have seen this quite a few times. So now we'll directly write this result, right? So we'll directly write that result here. So it is equal to times half times del of, right? So maybe as we don't have a space here, right, I'll write the remaining part here, right? So everything comes inside the summation. So it is del of f minus, instead of fc, if you see here we do have, right, fc plus nfm, right, fc plus nfm. So instead of minus fc, I should write minus fc minus nfm, right, then plus del of fc f, oh sorry, control z, f plus fc plus n fm. So it became messy. I'll rewrite it here, right? So our s of f, right, our s of f is equal to, so this 1 by 2 I am taking out, right, ac by 2 times summation n from minus infinity to infinity jn beta times, right, so we do have del of f minus fc minus n fm plus del of f plus fc plus n fm, right, where fc it is carrier frequency, fm is message frequency, and n will span from minus infinity to infinity. So we are getting something. So del of f is an impulse function, right? So we will get, right, so there will be infinite components, right? So there will be infinite frequency components spanning from n equal to minus infinity to plus infinity, right? So one will be actually what del of, before n is equal to 0, it will be actually what del of f minus fc and del of f plus fc, that will be corresponding to carrier, right? For n equal to 1, it will be del of f minus fc minus fm. So what we have is, so the detailed spectrum in next session, right, during Saturday's live session we will see. But for instance, right, just take this final spectrum of wideband FM, right, and if we approximate, right, beta is very small. If beta is very small, right, Jn of beta will be 0 for n greater than 2, right? So just keep this, try to accept this comment now, right? I'll explain it in detail in next session, right? So if we are approximating beta is very small, right, this Jn beta, so I'll just write, if beta is very small compared to 1, right, Jn beta will be, Jn beta will be equal to 0 for n greater than 2, right? So what happens is that reduces to what, the expression for narrowband FM. Maybe we can try, right? So that will reduce to spectrum of narrowband FM, right? So when beta is large compared to 1, then it is actually what, wideband FM, right? It will have ideally it will have infinite frequency components, right? So which will be on either sides of FC, right, and minus FC, right? So that's what we have. So now I'll just show you what actually is this Jn beta, and we'll wind up today's session. So before that, I'll just have a quick recap. So the root is, right, so initially we have written the expression for s of t, then we have written s of t as a function of s tilde of t, right? Then what we did is we found the Fourier series expansion of s tilde of t, right? Then using that, right, using that Fourier series expansion of s tilde of t, we found actually what, Fourier series expansion of s, not exactly Fourier series expansion, but using Fourier series expansion of s tilde of t, we found the s of t as weighted sum of sinusoids or cosinusoids. Then we took its Fourier transform. Then we took its Fourier transform. Right. That is what is this. So this is a bit lengthy derivation. So as it is a recorded session, I have done it a bit fast. So you please take time and pause in between, take notes along with whatever steps I have written, so that it will be easier for you. And whatever mathematical prerequisite exactly required for this particular say topic I have mentioned, right? So if you are not clear about complex exponential, complex low pass equivalent, you don't have to go there. Definitely you are going to study that in 6 semesters. And for instance, whatever is required for you, right, I have given, right? Maybe in another tutorial session or a doubt clearing session, if you want more insights on this complex envelope of bandpass signal, right? So I'll give that more in detail. Now I'll just tell you how and what actually is this Bessel function, how it will change. For that, I'll just right, yeah. Give me a moment. Right, I'll just take this. I have this narrow. Okay, this is actually what you can see Bessel function. I'm just opening it. Yeah, please hold on. Yeah, so this is actually what Bessel's function. I have plotted j and beta along y-axis and beta along x-axis, and these different curves, if you can see my mouse pointer, that corresponds to actually what different order. You can see j0 beta, it is actually what a damped, it's something like a damped sinusoid, right? And all others are starting from 0, right? And as beta changes for a given n, right, j and beta changes, right? Please note down, as beta changes for a given n, you can see j and beta changes. And also as order changes, right, for a given beta, j and beta changes. So this is actually what the Bessel's function. So these will be the coefficients of actually what individual say harmonics or individual components of the spectrum, right? So with that, we will conclude today's session, right? So I request everyone to like watch this video, pause it, take down notes along with this, right? So it's a very important result which you have derived. So maybe the physical significance or the spectrum interpretation of this particular result we will do in next session, that is in next live session. So before the next live session, I request everyone to watch this video. So that's it for today. Thank you so much.